Let's start with the topic limits. The first important point to note is that limit of a function fx is said to exist as x tends to a, okay, when limit h tends to 0 plus f of a minus h is equals to limit h tends to 0 minus f of 0 plus, this is 0 minus, I'm sorry, this is 0 minus f of a minus h, and limit h tends to 0 plus f of a plus h. This is equals to some finite value. Let's say k. Okay. Now, this is called the left hand limit, and this is called the right hand limit. Why right hand? Because it is 0 plus. If it is 0, then this will be 0 plus, this will be 0 minus. Okay. So, limit h tending to 0 minus f of a minus h, and limit a tending to 0, h tending to 0 plus f of a plus h. Both limits should be equal, and they should equal some finite value k. Okay. Now, the second point is indeterminate forms. There are 7 indeterminate forms. First of them is 0 by 0, infinity by infinity, 0 into infinity, infinity minus infinity, infinity to the power 0, 0 to the power 0, and 1 to the power infinity. Fine. These are the 7 indeterminate forms. Let me write it. Indeterminate forms which we come across in limits. Example for this is x by sin x, limit x tending to 0. Now this is x tending to 0, okay? This is x tending to 0. Now, the numerator is 0, tending to 0 when x is tending to 0. Sin x also tends to 0. So that's why this is a form of 0 by 0. Just like this, infinity by infinity can be like this, ln x, and limit x tending to 0. So this will be infinity by infinity. Fine. So this is a form of indeterminate. This is a form, indeterminate form. One of the indeterminate, 7 indeterminate forms. So, how to calculate this? So, there is third point, standard limits we have achieved through some formulations. Standard limits, which we can use, to calculate this type of indeterminate limits, forms. So, the first of them is limit x tending to 0, sin x by x is equals to limit x tending to 0, tan x by x, this is 0, okay, is equals to limit x tending to 0, tan inverse x by x, which is equals to limit x tending to 0, of course sin inverse x by x, because these are similar functions, tan inverse x and sin inverse x. So that's why, and is also equals to limit x tending to 0, e to the power x minus 1 upon x, also equals to limit x tending to 0, ln 1 plus x, okay, ln 1 is 0, and then upon x. These all limits are equals to 1, okay. Now, we'll see these are the standard limits. Sin x by x, x tending to 0 is a form of 0 by 0 indeterminate form. Okay. This is also 0 by 0. This is also 0 by 0. This is also 0 by 0. This is also 0 by 0 and this is also 0 by 0. All these 0 by 0 forms tends to 1. Now the second one amongst this is limit x tending to 0. We have 1 plus x to the power 1 by x. Now this will be 1 to the power infinity, because 1 plus x when x is tending to 0 is 1 and 1 by x will be infinity. So this is 1 by infinity, 1 to the power infinity form. Okay. Now this is equals to limit x tending to infinity 1 plus 1 by x to the power x. This is also 1 to the power infinity, because 1 by x when x is tending to infinity is 0 and 1 plus 0 is 1. Fine. So 1 to the power x is infinity. So 1 to the power infinity form. These two equals e. Third set is limit x tending to 0 a to the power x minus 1 upon x. When x is tending to 0, a to the power x will be 1. A to the power 0 will be 1. So 1 minus 1, that is 0. Right? And upon x, that is also 0. So it is 0 by 0 form. This is equals to log a. Remember the difference between a. This a is a constant. So log a base e, and a is greater than 0, of course. Then only you can apply this. Fine. Now, limit, fourth form, limit x tends to a, x to the power n minus a to the power n upon x minus a is equals to n a to the power n minus 1. Example for this is x square minus a square upon x minus a. Limit x tends to a. Now this is 0 by 0 form, because when x is equals to a square minus a square, the numerator becomes 0 and the denominator x minus a becomes 0. So this is 0 by 0 form. Now this is equals to n a to the power. N is 2, a to the power 2 minus 1, that is 1. So this is equals to 2a. This is how we calculate this type of limits. Okay, these were some standard limits. Now we'll see the limits using expansion. So limits using expansion. We'll see some expansions here. First of them is a to the power x. The expansion for a to the power x, you need to remember these, because these 6, 7 or 10 expansions, these help in, many questions. Not only limits, but also in many other questions like integration, differentiation, binomial theorem. You can use them in many fields. So 1 plus a to the power x is 1 plus x ln a by 1 factorial. Factorial is n factorial is 1 into 2 into 3 into 4 into up to n. Multiplication of n terms, n natural numbers. X ln a plus x square l square ln a square 2 factorial plus x cube ln cube a upon 3 factorial plus up to infinity. Okay, and here a is greater than 0, of course. Okay, now e to the power x is equals to, this is for a to the power x. This is the expansion for e to the power x, which will be 1 plus, when ln of e will be 1, so that's why all ln a will become 1. So that's why 1 plus x by 1 factorial. This is the simplest expansion, and you can derive any expansion from e to the power x. So that's why, from a to the power x, sorry. So 1 plus x by 1 factorial, ln a will be 1, x square by 2 factorial, ln square a will also be 1, x cube by 3 factorial, and plus up to infinity. This is the expansion for e to the power x. Third one is for ln 1 plus x. Ln of 1 plus x. This is equals to x minus x square by 2 plus x cube by 3. This is also simple. X to the power 1 by 1, x to the power 2 by 2, x to the power 3 by 3 minus x to the power 4 by 4, and alternate plus minus sign. Plus minus plus minus. Okay. Up to infinity for x from minus 1 to 1. Okay. You can only apply this in this range and can be equal to 1. ln 2 is also expressed in this form. So this is the ln 1 plus x expansion. Now we'll see sin x. sin x is equals to x minus x cube by 3 factorial plus x to the power 5 by 5 factorial minus x to the power 7 by 7 factorial plus alternate signs plus minus plus up to this up to infinity. Fine. Now cos x, well, you can derive cos x from sin x also by differentiating it. So it will be 1 minus x square by 2 factorial plus x to the power 4 by 4 factorial minus x to the power 6 by 6 factorial up to infinity. You have to differentiate this series. Okay. This also has plus minus signs. Fine. This is plus minus plus alternating signs. Now next formula is for tan x. Tan x will be x plus x cube by 3 factorial, x cube by 3 plus 2x to the power 5 by 15. This is hard to remember and it's also not used many times. So if you can remember it, that's good for you. If you cannot, that's also good for you. So tan inverse x, next one, x minus x cube by 3 plus x to the power 5 by 5 minus x to the power 7 by 7. This is just like the sin x series, but factorial is not included. Okay, so you can remember it like that. Factorial is not included plus this factorial is not included. This is not 3 factorial, okay, not 5 factorial, not 7 factorial. This is only 7, 5 and 3. Okay, so this factorial is not included in the sin series. Then you can have tan inverse x series. Now the next one, which is sin inverse x, is equals to x plus x cube by 3 factorial plus this 1 square, right? 1 square x cube by 3 factorial, then 1 square 3 square by 5 factorial x to the power 5. This is also hard to remember, so if you can remember, then it's good. Okay, x to the power 7 upon 7 factorial. This is just like 1, then 1 3, then 1 3 5, then next term will be 1 3 5 7, and like that. And these powers will be just the next number. If this is 1, then this will be 3. If this is ending at 3, then this will be 5. If this is ending at 5, then this will be 7. And the power will be the factorial downwards at the denominator. This will turn up to infinity. Fine. So these are the 9 important relationships. Now the most important of all of them is 1 plus x to the power n, which is used in the whole binomial theorem. This can be written as 1 plus nx plus n minus 1 by 2 factorial x square plus n minus 1 n minus 2 by 3 factorial x cube, and just like that up to infinity. This is the expansion for 1 plus x to the power n series. Okay, and here for all mod x less than 1, okay, x is between minus 1 and 1 and not included 1 and minus 1. Okay, you cannot include 1 and minus 1 in here. So this and n belongs to R here. N can be anything. So these were the 10 expansions I want to tell you about, and now we'll see some limits of the form 1 to the power infinity, limits of the form 1 to the power infinity, 0 to the power 0 to the power 0 and infinity to the power 0. These forms. So for like limit x tending to 0, 1 plus x to the power 1 by x is equals to e. Similarly, limit x tends to the power a, x tend to a, fx. Let's say we have some fx and we have some gx here, where for 1 to the power infinity types, I'm telling you about 1 to the power infinity types, if fx is tending, where fx is tending to 1 and gx is tending to infinity. Fine. Now, also, of course, when x tends to a, for this function, for this limit, this implies limit x tends to a e to the, it will be limit, this limit will be equal to e to the power limit x tends to a, this one into fx minus 1, will subtract 1 from the fx function and will multiply the gx function here. Okay, so this is how we solve it. I can take one example. Let's say we have ex, e to the power x, to the power infinity, let's say 1 by x. Okay, so limit x tending to 0, we have this function. Now, whenever you have a function like this, or let's say we have x plus 1 instead of this, so let me rub it. Instead of e to the power x, that will be simpler. Now, instead of that, we have x plus 1. Now, when x is tending to 0, x plus 1 is tending to 1, and 1 by x is tending to infinity. So, this is 1 to the power infinity form. So, how to solve it? We will solve it using this. So, what is e to the power limit x tending to 0? This limit will be equal to fx minus 1. What is fx minus 1? X plus 1 minus 1, that will be x into gx. Gx is 1 by x. So, this turns out to be 1. And limit x tending to 0, 1 will be a constant, that is 1. So, this will be e. So, that's our limit. When x plus 1 to the power 1 plus x. When x is tending to 0. So, this is how we calculate the limit. Okay. You can have the e to the power x also, e to the power x minus 1 by x. Then you will have limit x tending to 0, one of these standard limits, which is 1. So, that way you also get e to the power 1, that is e as answer. So, this is how we solve the 1 to the power infinity, 0 to the power 0 and infinity to the power 0 limits. Fine. Now, let's move on to the sandwich theorem and squeeze play theorem. Sandwich theorem or squeeze play theorem. Fine. Now, sandwich theorem and squeeze play theorem says that if you have three functions like fx, gx and hx, and they satisfy this type of condition, that fx is less than equals to gx is less than equals to hx for all x. Okay, if they satisfy this type of condition, then limit x tending to a is limit x tending to a fx is equals to L, which is equals to limit x tending to a hx. If you have these conditions, okay, these first condition and this second condition, then this implies that limit x tending to a of g of x, which is in the middle of both of them, that will be also L. Okay, if the function fx and hx are tending to L, some limit, some constant L, when x is tending to a, then limit x tending to a, gx will also tend to L. If gx is in between these two functions, is sandwiched between these two functions, is squeezed between these two functions. That's why this is sandwich theorem. Because when a function is sandwiched between two of the other functions which are tending to a same limit, when x is tending to a, then x is tending to a, gx will also be L. Okay, this is the sandwich theorem. Now, L'Hospital's rule, which is the most important rule, which can be applied to any of the limits. And okay, so this rule states that if limit x tends to c, fx is equals to limit x tends to c, gx is equals to 0 or plus minus infinity. In these cases, like 0 by 0, infinity by infinity, these type of cases, how to solve them? So, and limit x tending to c, f dash x upon g dash x exists, then limit x tending to c, fx upon gx will equals to limit x tending to c, f dash x upon g dash x. Why is that? This L'Hospital's rule says that if you have some function which at x tending to c, another function gx which at x tending to c, they both equal 0 or plus minus infinity, then this forms will be either 0 by 0 or plus minus infinity by infinity. Okay, so that limit will equal to limit x tending to the same variable, the same constant, and f dash x upon g dash x. Okay, so this is the thing. We'll take one example in here. Example. Let's take one of our standard limits, e to the power x minus 1 upon x, limit x tending to 0. Now this is our fx and this is our gx. Fine. Now limit x tending to 0, fx is what? 0, and limit x tending to 0, gx is also 0. So this is 0 by 0 form. Fine. Now what does the L'Hospital rule says? It says that if you have two of these limits which tending to 0 or plus minus infinity, then do f dash x and g dash x and see if this limit exists. So we'll just differentiate both the functions. What would be the differentiation of e to the power x minus 1 with respect to x? Okay, whatever the limit says. So limit x tending to 0, e to the power x minus 1 upon x will be equals to limit x tending to 0, e to the power x minus 1, differentiation of e to the power x minus 1 is e to the power x upon the differentiation of x is 1. Now when you put the x equals to 0 in this function, this will give you e to the power 0, that will give you 1 as the answer. And we have the standard limits of e to the power x minus 1 upon x as 1. So that's how we calculate this. L'Hospital's rules applies on something like this also. Let's say we have to calculate sin x upon x. This is also 0 by 0 form. Fine, indeterminate form. So you differentiate it with respect to x. Sin x, differentiation of sin x is cos x. Sin differentiation of x is 1. So cos of 0 is, you put x is equals to 0 in this. So cos 0 is 1. So this is also your standard limits, one of the standard limits. So this is how you use the L'Hospital's rules. L'Hospital rule. One important condition is this is that if you get an indeterminate form with the f dash x and g dash x, limit x tending to 0, this also, if you get a indeterminate form in this also, then what we'll do, we'll once again differentiate it and keep differentiating until you get the constant limit. As a constant limit, until you get a constant limit, you have to differentiate it again and again. This will be iterative solution. Okay, now the next topic for this is the last point for this. If f and g are polynomial, trigonometric, or exponential functions such that g of a is not equals to 0. Okay, f and g are polynomial, trigonometric, logarithmic, or exponential functions such that g of a is not equals to 0. Then limit x tending to a, fx upon gx will be fa by ga, provided that fa and ga both are not infinite or not defined, are not infinite, and a belongs to the domain of f intersection domain of g. Okay, you have to find the intersection of both the functions domains, and you have to see that a belongs to that set. If a belongs to that set, then this limit will be fa by g. Just put the value of a. Okay, so here we complete our limit section. We will continue with continuity and differentiability.